predicates and quantification. Predicates and quantification. Let me see, maybe, okay, I can admit that, not me, this guy. So you can see that arguments. So you notice that this is an advancement of what you did last time with respect to mathematical logic. And we told that an argument is an assertion that a given set of propositions. When you're talking about set of propositions, just statements, and those ones are called the premises. These ones yield another proposition called a conclusion. And you notice that, for example, here we're talking about that is P1, P2, P3, all the way to Pn. When we have all these, then you realize that all this, the conjunction of all these lead us to some conclusion. You see, that is what we mean by an argument, that you have a set of propositions, and those propositions, of course, are combined using logical connectives. And when you have those logical connectives, not necessarily only conjunctions, could be even in terms of biconditions, could be in terms of disjunctions. And I think you still remember exactly what a disjunction is, what a conjunction is, what a biconditional statement is, what a conditional statement is. That is very important. And you notice in that case, when we have all these combined together, then they give us, we make a conclusion out of all those. All these are the ones that are called the premises, right? And we say that an argument of this nature is said to be valid if Q is true whenever all the premises, all these others are true, you see. And an argument which is not valid is called an invalid argument or a fallacy. So for us to have a clear view of this, and I think it is important that we look at now, that is, of course, how to go about. And here we say that that argument is valid if and only if the proposition is a tautology. And in this case, it is the whole of this being a tautology. Of course, you see we have some implication at some point to lead us to this conclusion. So let's see some few. Look at this. We have P conjunction P, that is implication Q, implies Q. So we would want to see whether, yes, does this really lead us to what we call that is a tautology or not? Look at this here. This is what we're talking about in as far as A is concerned. You see, P conjunction P, look at this, P implication Q implies Q. So one way of determining the validity of such a statement is by use of the truth tables. And that is exactly what we shall confine ourselves in. If anything, I think what I'll do, I would advise you not to bother much about what you call rules of inference. Rules of inference are a bit involving and at the same time require a lot of cramming in as far as the different rules of inference are concerned. And I think you see this, of course, there ahead. So look at this here. We have P, comma, P implication Q. Of course, we have that the conclusion is Q. And we call this the law of detachment. But you don't have to remember that this one is called the law of detachment. What we need to know is how do we go about in testing the validity of this proposition. You see, this one is a compound proposition in itself. And of course, we call this an argument if it is presented in this manner. Yes, where this and this are two premises, this one and this one make up two premises. And then, of course, we know very well that this second premise is in itself, that is a compound statement. Of course, a combination of P and Q using the implication P implies Q. And then, of course, this represents, that is implying, therefore, you see this one now leads us to the conclusion that once you have the conjunction of these statements, then it implies Q. So what we need to do in as far as the truth table is concerned is what we did last time. It is no different from that, exactly what we did. And you can see in this case, and I think you remember this very well, of course, we have P and Q. And what we see in this case is that we consider all combinations of the truth values, true, 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 false, false, true, false, false. And then, of course, when we talk about an implication, it can only be false when the first one is true and the second one is false, and true otherwise. And that is exactly what we see here. True implication true is true. True implication false is false. False implication true is true. False implication false is true. And now what we need to do is to have the conjunction of this one and P. And of course, when you talk about a conjunction, it can only be true when both are true and false otherwise. So true, 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 you can see that gives us true. Of course, it is this, the conjunction of this and this one and this one. True, true, that is true. This one and that is false. This one and that is, let's look at that carefully. Let's see, no. Yes, that is okay, yeah, that is true. This one, false and true, that one is false. Of course, false and true in that case is false. And I think you still remember very well when you're talking about a conjunction. Now we have all of these. We would wish to see now this one, implication Q. And we know again that the implication this implication this can only be false if this one is true and this one is false, going by what implications are. So true implication true is true, false implication false is true, false implication true is true, false implication false is true. And that is why we have all this here. You can see that right here, this last column. And we see that all of this therefore is a tautology. So we conclude that the argument is valid. And you can see that here. Now, what happens if we come across problems in words instead of, you see, given instead of symbols? You see, we've used the symbols here. How do we have an argument presented in words? This is how it is presented. You can see, this is the premise. This is what we call a premise. If I like discrete maths, then I will study. S2, this is the second premise. Either I study or I fail. So how many statements do we have here? We have, I like discrete maths. I will study. Yes, I study is the same as I will study. I fail. So we have three statements there. And you notice that here, I fail is exactly as the one that we have here. I don't like is the negation of I like discrete maths. You can see don't like is negation. So how do you present those ones? Look at this. Look at this. We've decided to let I like discrete maths be P, I study be Q, R, I fail. And now going back to this statement here, we see that if I like, you see this is an implication. If I like discrete maths, then I will study. So if you see, I like discrete maths is P, implication, I study, yes, P implication Q, and that is exactly what we have here. Look at this. When we have either I study or fail, all or is a disjunction. Let me hope that you remember that. Or is a disjunction. How do you represent that disjunction? I think you see this one is, and then you see this one is, remember this one is P, if P, then Q. And then here, you see I study, that is Q, or I fail R. We've called I fail R, if I'm not wrong, yes, that is it. So that is why you can see here. P, if I like discrete maths, then I will study. I study or I fail, you see, or represented by disjunction. And I think you still remember that. And then now the conclusion is, look at this. If I fail, the conclusion is in the form of an implication. If I fail, which is R, imply negation P, because I like discrete maths is P, but I don't like is the negation of P. And that is exactly what we have here. You look at that. R, meaning I fail. If I fail, then I don't like discrete maths. Yes. If I fail, then I don't like, because P represents I like. So how do we rewrite this using the different connectives? We have the first premise here, conjunction, the second premise should imply the conclusion. This one is the conclusion. You see, that one is the conclusion. And that is exactly what we have here. You can see this one is here, conjunction this, and then implies R, that is implication negation P. So how do you go about this? Look at this. Remember here we have three propositions. If there are three, I think I mentioned this last time, P, Q, R. So we have true, true, true. And then now we have one false. We introduce in the form of a diagonal one false. And therefore you see just one false. You can see this. And then these are just true, 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 true. And then now the next part is having two false and one true. Do the same again, just like in a way where you introduce a diagonal, you can see that. So we have true, true, and of course these are that's false, 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 and then finally the last one is when all of them are false. And in this case again, of course, an implication is only false when the first one is true and this one is false. So this one is true, this one is true, this one is false. You can see that this one is true, this one is true, this one is true, this one is false. Disjunction. Sorry for that interruption. Let me hope you can hear me. Sorry for the interruption. Let me confirm whether you can hear me. Just one of us to raise his or her hand. Oh yeah, thumbs up. That is okay. Yeah. Okay, that is okay. Thank you. So we have Q disjunction R. A disjunction is only false when both are false and true otherwise. So we see this one Q disjunction R. So we have here Q disjunction R. True, 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 true. But this one is false because both are false. This one is also you can see that. This one and that is false. This one and that true. You can see it, conjunction of that and that is true. Conjunction of that true, true, true. This one and that false. Conjunction of this and that is false. You can see. Now what we need is R implication negation P. We must get the negation of P, and that is why we have negation of P here. So we have implication. Implication, of course, you see, is only false when R is true and negation P is false. So we have here this and that is, look at this carefully, that is false. This one is true. This one is false. No, no, it is here. That means, let's see that this one and this one is false. Yes. This one true, true, true. This one true implication true is true. False implication true is true. You can see that. False implication false is true, which is here. False implication true is true. And that is why we have that. Now, what follows? What follows is this one, implication this. So this one, implication this, can only be false when this one is true and this one is false. So this one, implication this, is false. That is why we have false there. This implication that is true. This implication false is true. True implication true is false. True implication true is true. True implication true is true. False implication true is true. False implication true is true. And now we see that we have one F here. At all these being true, then we could have said that it is a valid argument. But because now it's a mixture of false and truth, then we say that it is an invalid statement. So this is in as far as the use of the truth table is concerned in determining the validity of an argument. We have another way of determining the validity of an argument. We use what we call rules of inference. And this is what I've decided instead of taking you through this process of memorizing all these rules of inference, all these ones, you realize that all these are valid arguments. And these are recognized arguments that are called rules of inference. And these ones help us in making conclusions whether certain arguments are valid or not. Excuse me, please, just a minute. A minute. Yes. Somebody addressed his hand. What could be the issue? Any issue? There seems to be none. Huh? Okay. But you can hear me, right? Yeah, there was some brief interruption. Can you hear me? Just raise your hand if you can hear me. Thank you. Okay. It's important that we be together there. So we see that these rules of inference, you see, these rules of inference are the ones that help us also to make conclusions about the validity of arguments. You see, they are used to draw conclusions from other assertions or hypotheses. You see, they simply provide a justification to show that a conclusion follows logically. Therefore, if it is following logically from a set of hypotheses, then we say that that is a valid statement. We have others that are invalid. So you notice that all these are tautologies. They range from what we call addition, simplification, modus ponens, modus tollens, hypothetical syllogisms, disjunctive syllogism, all the way to resolution. But now, you see, that is why I tell you guys to be very keen. When you have a simplified version of a unit, do not take that for granted. As the way I've seen, you see, I've seen that you guys at some point, you are not very, very keen. I am making a very serious plea that you be very keen and please make use of that gesture made by your lecturer to simplify the unit, to make it more understandable. And at times even deciding even how to take you through, especially those areas that involve a lot of memorization. Like in this case here, you see, I'm equipping you with this, but what you do in this case is that you just have this for your consumption and of course for application to whatever that you'll do there. There'll come a time that you use these rules of inference, you see. But what I'm saying in this case is that, well, because it takes a lot of, you see, it requires a lot of memorization to have modus ponens, modus tollens, simplification, and so on. In using those ones to determine the validity of statements, like in this one, you can see here, we see that this one is the hypothesis, and we see that it gets us to this by simplification. And when we have this, of course, conjunction, you see P implication Q, we conclude that it is Q because of modus ponens, you see. Such, you find that all these leads you to this conclusion by how many rules of inference? We have two rules of inference here. We have simplification and modus ponens. You see, like in this case, you see, we translate this into symbols. Look at this. The first thing is translating this into symbols. And then after translating to symbols, make an argument out of that. Then test the validity of that argument. You can see what we've done here. It is raining. We've called R, we will go for swimming. We've called it T, we will reach home by sunset. And then now we have now the statement here. You look at this. We have this, R implication that, negation R implication S. and then S implication T, and then at the conclusion is T. So what we need to do is to use the rules of inference to determine the validity of this statement. And you notice in this case, look at this, we have P implication Q. By simplification, it is negation P. And now when we have negation P, conjunction R implication P, which is this one, we see that by modus tollens, it gives us negation R, and then negation R now that we have obtained here, conjunction this, we see that that gives us, there is S by what you call modus ponens, and then S conjunction S implication T, that is the hypothesis. How do we conclude this? We conclude that it is T by modus ponens. So you see this one is involving, and at times you find that it may require a lot of memorization, which may not be necessary, especially at your level. And that is why I would ask you, ignore this. There is the rule, or the use of the rule of inference in testing the validity of the statements. Just stick to the one that we use, what you call the truth tables, like these ones that we've used in these two. That is it. This one, that is it, and this one. So we are good in as far as that is concerned. What I would want to do now is to take you through what to call predicates and quantifiers. Predicates and quantifiers. And I need your keen attention in as far as this is concerned. A very keen attention. Under predicates and quantifiers, we would want to know exactly what predicates are. And we start by saying that there are some logical notions, look at this, which are helpful in symbolizing mathematical language or computer programs in such a way that make possible an analysis of an argument. Look at that. And our main idea in this case is to test the validity of a certain argument. And even in programming, you find that there are some areas of programming that will require you to know what predicates are and quantifiers. So we start from a very simple point of view. And here, we're starting by considering these statements. X is less than 7. X plus Y is equal to 9. X plus Y plus Z is equal to 6. Suppose I ask you, can you determine the truth values of this? I think the answer outrightly will be no, because I don't know what X is. Also in this case, the answer is no, I cannot determine the truth value of this statement because X plus Y, I don't know what X plus Y. But once I'm given the value of X, then I can determine whether it is true or not. That is it. And you find that these statements change from, in fact, just statements to propositions. Remember, propositions that can either determine, whose truth values can be determined, either true or false. And that is exactly what we're saying here, that these statements are neither true nor false, unless the values of the variables are specified, and that is it. And we're told here there are some ways by which propositions can be produced from such statements. And what are these ways then? You see, that is the big question here. We are asking ourselves, what are these ways? So let's see. We find that these statements like X is less than 5 or X is less than 7, as we've mentioned here, has two parts. We have X as stands on its own, and then is less than 5. You notice that this is the property that we associate X to. You see, X is a variable, and this less than is exactly what we call a predicate. Is less than 5 is a predicate. X is a subject of the statement, and that is exactly what we've mentioned here, that X is the subject of the statement, and the second part, which is less than, is actually what we call the predicate. And a predicate actually allocates or gives the property that the subject of the statement must have or may have. So therefore, we say that a predicate is a word or a set of words in a sentence which express the nature of the subject. And that is it, of course, when you're talking about this nature, basically we're talking about the property. And we say that a predicate is supplemented by including a variable. We must include a variable like X, like Y, and so on, as a placeholder for the intended subject. Thus, we denote the statement X is less than 7 by this. P is actually the property, X is the variable. You can see that that property is the one that we call predicate. And it's less than is actually the predicate, and x is the variable. So that if we have, let's say, a certain value of x here, then we say that, by the way, we call this a propositional function. P of x is a propositional function. When we have the value of x, then that propositional function changes from a propositional function to, in fact, a proposition whose truth value can be determined. You see, this one is a propositional function. It is not a proposition. But if we have a certain value of x, then it becomes a proposition. And that is exactly what we have here. That once a value has been assigned to the value of the variable x, px becomes a proposition, and therefore you can find its truth value. Let's look at some examples here. Let p of x be the statement x is greater than 11. You are asked to determine the truth value of p13, p13 and p9. Of course, p13, we floating 13 here. 13 is greater than 11, and therefore that is true. And you can see that. 9 is greater than 11. No, that is false. And that is why we say that p9 is false. You see? To extend further, we say that we can also have statements involving more than, it doesn't have to be one variable only. Like this, of course, this wasn't one variable. And I think in some of the examples, you can see this one is denoted p of xy, p of x comma y. This one, p of x comma yz, look at this, yz. This one should be capital. So you can see this one is xy. Of course, this one being one, that is p of x. You see? What is happening here? This one is p of x. And see that. So look at this, and that extension comes to this. You can see we've called it q. It doesn't have to be p. And in this case, let q of xy denote, this one is a propositional function, x plus y is equal to 10. You're asked to determine the truth values of, that is q37, q38. And of course, this one is x and this one is y. 3 plus 7 is 10. 10 is equal to 10. That is 2. You can see that. But now this one, 3 plus 8 is 11. 11 is not equal to 10. So 11, look at this, 11 is equal to 10. That one is false. That is it. It's just that simple. And then we have an example here. This one, p of x, y, z. This one is a propositional function. We denote x is equal to y plus z. What are the truth values of the proposition 3, 2, y, 1? Like in this case, our x, you see it goes by that order. X is equal to 3, y is equal to 2, z is equal to 1. So we shall have 3, 2, 1. 3 is equal to 2 plus 1. Yes, this one is true. This one is true. But now this one, 2 is equal to 1 plus 0. No, 2 is not equal to 1. And therefore, that one is false. Now, we know what propositional functions are. Up to there, well and good. There is something else we need. But before I proceed, again, let me confirm that you can not only hear me, you can also, let me see those ones who can hear me. This is a test that is always important. Okay. Law, your hand. Now, let me see, Law. Then I have a second question. Can you see my screen? Perfect. That is okay. Let's continue. Now, let's look at this quantification. By the way, for your information, when you talk about quantification, quantification is not something that you don't know. For your information, quantification is something that we've used a number of times. You just remember, what does this, one of us tell us, what does this mean? And what does this mean? Even in the chat box, what does the first one mean?
For all.
Perfect. For all or for every. How about the second one? Yes.
Existing.
They exist. They exist. Yes, they exist. They exist. That is very true. And you notice that those ones are what we call quantifier. These are the ones that we call quantifiers. By the way, this one for all is what we call universal quantifier. This one is what we call existential. And when you look at those terms, you notice that in fact, the existential quantifier is derived from the existential quantifier. For all, it means all elements in a particular domain. But now when we talk about the exists, all we need is just one element. Suppose I say there exists, let's say when we're in class and I say that there exists one of us who is smiling. There exists a student who is smiling in this, let's say, class this afternoon. What all you're supposed to do is to just look for one person who is smiling, and you say, oh yes, our lecturer is, in fact, it is true that our lecturer saw that, yes, there is one person that has smiled. Now, when we say for all, now look at this. When I say, even, let's say in the lecture room, of course, our usual lectures in the afternoon, I say that there exists a student who is smiling. That is true at all times, by the way, for your information. I've never gotten into a lecture where I found everyone to be serious. There has to be at least one fellow who is smiling, and that is always the case. And therefore, the chances of that being true are very high. Of course, we don't go by chances in that case. We simply say that that is a true statement. But when I say that for every student of SST 102, that of course, let's say whenever we consider a smile, every student of SST 102 applies is not his false, because there are some fellows apparently even who don't know how to smile. In the group, there is a very high likelihood, that there could be some fellows who hardly smile, if anything. There are some even fellows who do not smile at all. So look at this. When you talk about quantification, we say that a propositional function becomes a proposition when all the variables in a propositional function are assigned some values. And the resulting statement has some truth value. Of course, that is what we've mentioned. We say that quantification is another way to create a proposition from a propositional function. And that is very true. You see, you come across a propositional function like this. This in itself is not, of course, we don't know the truth value of that, unless we allocate some values X, Y, and Z. And in this case, it is possible to do so using also quantification. And that is why we're told that there are two types of quantification, what we call universal quantification and existential quantification. Look at universal quantification. Exactly, look at what the symbol we're using. Exactly the very same symbol that we've been using all along. This is not new to us, but at least now we are having an enforcement into the usage of the same universal quantification. But when you talk about universal, you see the law of universality, if there is such a term, I think there is you see, when we're talking about all, you see, when you say that something is universal, it is more of including everyone. So universal quantification. So the universal quantification of the propositional function p of x is written for every x, comma px. Look at this. And we told that px is true for all values of x. Where do we get these values of x? We have what we call domain, or what we call universe of discourse. This one is, you can see this, domain. It is just like the domain for a function. Remember here, we've called this a propositional function. You see, this one is a propositional function. And that being the case, come to your mind, you did functions in calculus 1, and I believe you did it, of course, yeah, you've done it this semester. We see that for every function, there is a domain, you see. And now we see here where we get the values of x is what you call the universe of discourse or domain, whichever way, any can do, in which the proposition is true for all values of a variable, and not all the time. We have some situations where it's not true, therefore we say that it is false. And how do we write that? We write it this way: for every x, px, where for this one is called the universal quantifier. Look at this. Examples. A statement, every student in this class is intelligent, can be expressed as follows. Look at this. Let px denote x is intelligent. You can see that. You see, is intelligent is the predicate p, and x is, of course, a student in that class. X represents the student. You can see that. And therefore, the universe of discourse consists of the students in the class. You see, that is where we get a member of X. We get it from the class. And therefore, we see this for every X, Px is true. You see, in as far as this statement is concerned. Now, we look at this. Let Px be this statement, X plus 1 is greater than X. If the universe of discourse is the set of real numbers, look at this, any real number, I think this is true. Because whenever you pick any real number, X, of course, is the variable, but the universe of discourse is the set, the domain where we get this X from is the set of real numbers. And if that is the case, it always applies to every real number. Look at it. Isn't it true that when you increase any real number by 1, it will be greater than that original real number? Like 2 plus 1 is greater than 2. You see? And remember, our X in that case is equal to 2. That is always the case. Even 2.21 plus 1, it is always greater than 2.1, where X in that case is 2.1. So for every real number, whenever you increase any real number by 1, it will always be greater than that real number. And that is exactly what we say here for every X, Px is true. Now, let's go to existential quantification and see the difference. Here, all we need under existential quantifier is at least one element that for that statement to be true, for that propositional function, of course, which changes to a proposition after equipping with an existential quantifier, all we need is just one element that satisfies that property. For as long as that single element satisfies that property, we conclude that that is true. And we see this in this existential quantification. Look at this. The existential quantification of Px is the proposition they exist. You see? And of course, we know that is represented by that symbol. An element X in the universe of discourse such that Px is true. And it is denoted they exist such that Px is true, where this represents the existential quantifier. And this is what we know all along. And now the existential quantification, this is expressed as there exists an element X such that Px, yes. There is at least one X that satisfies that, and that is it. That is all we need. Look at this. This example, let Px denote the statement X plus 3 is less than 12. The universe of where the universe of discourse is the set of real numbers. Now, do we have any real number when you add to 3, it is still less than 12? Of course, quite a number of them. But all we need is just one. And you can see we've identified 3 here, which when we say 3 plus 3, it is, in fact, this one should be okay. We could have this to be 7. Let's have that to be 7. There is an error here. There should be 7 here, so that it is 7 plus 3 is less than. That is all we need. You see, just one element that satisfies that. And by the way, you see, in this case, you could be asked to determine the truth value of this. Look at this. No, sorry. We have look at this. Suppose I ask you, look at this. There exists X. Yes, that is what we're dealing with. But now, what is the truth value of this? Suppose you are asked, you're given this to represent Bx, yes, and then the universe of discourse to be the set of real numbers, and then you asked about this, and you also asked about this. You will say this one is true because you can only identify one element. When you add to 3, it is still less than 12. But for every real number, it is not true because you notice that there are some real numbers that when you add to 3, they'll be greater than 12, but not less than that. And therefore, this one will be false. In as far as this is concerned, this one is false. But this one is true because all we need in as far as existential quantifier is just one element that satisfies that. Let's go to B. Look at this. Qx denote X is equal to X plus 5. The universe of discourse is the set of real numbers. Since Qx is false for every real number, the truth value of the existential quantifier in this case is false because there is not even a single element that is equal to that element increased by 5. Akuna. None. There is no real number that will not change, that it will be exactly the same if you add 5. None. And therefore, that is false. Something to add up. This remark is when all elements in the universe of discourse can be listed, x1, x2, and so on, the universal quantification for every x px is the same as this conjunction. Look at this. Yes. Since this conjunction is true, if and only if all this, each one of these is true, that is for universal quantification. But when you talk about existential quantification, we use the disjunctions. You can see that. And for us to see this, look at this. What is the truth value for every x px, where px is the statement x squared is less than 26, and the universe of discourse consists of integers not exceeding 5. 1, 2, 3, 4, 5. So what we need to do here is to check on each one of these. 1 squared is less than 26, that is okay. 2 squared is 4, which is less than 26. 3 squared is 9, which is less than 26. 4 squared is 16, which is less than 26. 5 squared is, that is 25, which is less than 26. And therefore, that in itself, yes, this statement is true. Look at that. All this apply to this. All of them are less than 26. Now, for the case of the exists, where px is this, and the universe of discourse is 1, 2, 3, 4, 5, 6, it is also true. All we need to do here, it is either this or this or this or this. All we need to have is just one that is true. You see, this one or this is true. This one or this is true. This or this is true. This or this is true. Now, true or false, because we have or, we notice that it is still true, because a conjunction can only be false, no, a disjunction can only be false if both are false and true otherwise. And therefore, that is true. Now, there is something small here that I'd want you to, and I need to make some corrections here. I made some corrections here. There are some errors in as far as this is concerned. I may have to send, that is an improved. I noticed that there's some errors here. I may have to do this here. Yes, I think I corrected this. Kindly allow me to do this. You can see these ones. There are some errors in as far as I think, let me see that. Yeah, you can see here it is the universe of discourse is 1, 2, 3. 4 should not be there. 4 should not be there. You can see this 4 should not be there. You can see this 4 should not be there. You can see those ones. So, and I've made some corrections there. And the one that reflects those corrections should be here. Why is it not responding? But I think it will take a short time. We should be able to get there in a moment. Let me hope that my laptop is not hanging. Aye. My laptop is misbehaving. Want to see whether, aha, Mohoro Ngunjere right there smiling. Okay, for every, yes. Yeah, I like that. You see, yeah. Being interactive is good, you see. Yeah. Probably who could be smiling? Could it be Ngunjere? Let me see whether it has responded, unless it has issues. Why is it there? Oh yeah. I was wondering why is it giving me some issues. Yeah. Look at this here. Apparently my laptop is misbehaving a bit, but no worry. I think we shall get there. Yeah. Kindly please correct if you have those soft notes. But anyway, I'll send the improved version. It's no problem. Look at this. There is something that we're being told here. That many mathematical statements involve multiple quantifications of propositional functions involving more than one variable. The order of quantifiers is important. Look at that carefully. The order of quantifiers is important unless all the quantifiers are one type, either universal or existential. But if they're different, look at this. Determine the truth value of each of the following propositions of the following statements where 1, 2, 3 is the universe of discourse. And look at this. There exists X for every y such that x squared is greater than y plus 4. Here now, you're told that there exists x such that for every y, look at that, there exists, in fact, that is how it goes. There exists there exists an element x in this set such that for every y in the same universe of discourse, x squared is greater than y plus 4. Now, the question is this true? There is only one element such that when you square it, it is always greater than y plus 4. Is there any? And of course, y is obtained also from here. Look at this. Take an example. In this case, I did not even finish this. You can see this. There is also an error here. This one should be greater than, right? That should be greater than. Yes, you can see that. That should be greater than. There is also an error there. Look at this. So, is there any x when you square it? It is greater than some y obtained from here plus 4. Look at this. Look at this. If x is equal to this one is wrong. This one is wrong. This one is wrong. Look at this. Suppose talk of 3. X is equal to 3. Then 3 squared is 9. And it is greater than, suppose y is equal to, you pick y to be equal to 1. Yes. If y is equal to 1, then it will be 9 is greater than 5. And that is correct. So there exists an element in this set. You see? And let's see. Let's see whether this is true. For every, you see, again, you must be careful here. For every y. So meaning for every member of L, for each one of these, look at this. Do we have an x when you square, it is greater than y plus 4 for every y in this? Look at this. Every means all this must be included. So we have 1 plus 4. Is 9 greater than that? Yes. 2 plus 4. 9 is greater than 6. 3 plus 4. 9 is greater than 7. Yes. And therefore, it is true for all this. Of course, these ones are y is equal to all. When we mean for all, you see that applies to y. So these are the values of y. These are the values that y is taking. And you notice that, yes, that is true. Now look at this. For every x, meaning we must factor in 1, 2, 3 in all this. So we need 1 squared, 2 squared, 3 squared. So 1 squared will be 1 plus y squared is less than 18. Now, 1 squared plus y squared is less than 18. All we need in that case is just one case where that is true. And in this case, for every x, you see, so when it is 1 squared here, we have a y when we square and add with this, it is less than 18, yes, like y is equal to 1. That is okay. Now, that is true for x is equal to 1. For x is equal to 2, this one will be 4. Now, do we have any y? Because we need only just one y that satisfies that. Yes, y is equal to 1. Because this one will be 4 plus 1 will be 5, which is less than 18. That is okay. Now, let's look at 3 squared now. This one is 9. 9, is there any y that we can add to 9 and it is still less than 18? Yes. One of them is y is equal to 1. Even y is equal to 2. All we need is just 1. So this one is true. Yes, it is true. And I will leave these two. As I said, I've modified this, and therefore what I'll do in this case is to send you this modified version. So that you can follow through these other two. Maybe let me do the third one because it deals with 3. Look at this. For every y. Now our point of focus here is for every y. So we need 1 squared, which is 1, with 2 squared, that is 4, we have 3 squared, that is 9, because for every y in this. So it means we must include all this. So 1 squared, 2 squared, that is 4, and then 9. There exists x and z. There exists x and there exists z, such that, of course, x and values of x and values of z are obtained from 1 to 3. Do we have such a case? All we need is just one case. Of course, 1 squared, here that is 1. In fact, the one that it could be trickier is the highest, which is 3 squared, which is 9. Now, if we have this to be 9, even this one, 2 squared, maybe 1 squared, that is okay, because let's say 2 squared is 4, plus 9 is 13, plus 1 is 14. It is still less than 20, and therefore that is true. It is true for all this. Y is equal to all this, yes. Because when we have 1, 2 squared, that is 4, 3 squared, that is 9. In all those cases, there are values of x and y. When we square them and add them, we shall always have that number here less than 20. I think we are done. Thank you for that. We are done with this topic. We shall now, in our next part, we shall deal with what we call Boolean. We shall introduce ourselves to Boolean algebra, a short topic, and then after that, we shall cross over to what we call the last topic, which is graphs. We shall deal with some graph theory, and that will mark the end of our unit. So we are drawing close to the. Oh yes, you are Kangai. For your information, you have the notes. But what I'll do is that I'll send the corrected ones. Yeah, I'll send them through to your representative. If anything.